This is Team 33's emulation gate report 4.5. Our project focuses on developing an energy-efficient, space-saving, and cost-effective spiking neural network solution to meet the needs of modern AI applications. The goal is to design an SNN with lower power consumption and reduced space requirements compared to existing models. Key features include an analog circuit design for improved efficiency, seamless integration with motor drivers, and a scalable, compact PCB implementation. Additionally, we incorporate a Raspberry Pi-based error measurement for real-time system monitoring. The final outcome is a pre-programmed dedicated SNN solution tailored for the automotive and autonomous industries, offering energy savings, ease of application, and a step toward more efficient AI-driven automation. The project is made possible by David Owen, Daniel Ainley, Madison Freeman, and Omar Mustafa, each bringing their expertise to different aspects of the design and implementation.
All right, so to cover our scope of work and our methods, there are two main challenges that defined our scope of work. Challenge number one was adapting the FPGA-based spiking neural network to a fully analog circuit while ensuring continued seamless interfacing with motor drivers and function parity between the different versions. The second challenge was taking that analog breadboard circuit and transferring it onto a PCB design using OFETs. This required adaptation of analog interfaces to fit the new OFET design. For our technical approach, we are using an iterative method to reaching our goal, in which the path we take sacrifices directness so that each step stands as a proof of concept for the next. This is exemplified in the above challenges that define our scope, where each step verifies that the next step is possible. Some assumptions and constraints for our project. An FPGA was used as a stand-in to emulate a theoretical analog circuit. This was done to verify that the SNN concept would in fact work and could be recreated in analog formats without digital logic. Additionally, digital weights with no direct correlation to physical voltages were used in the FPGA implementation as a proof of concept for our approach.
SNNs closely mimic how the human brain processes information. Unlike traditional models, neurons and SNNs communicate through discrete spikes, computing only when they receive input. This event-driven approach, shown in the diagram on the left, makes SNNs highly efficient in both power consumption and real-time decision-making. The key application is in autonomous vehicles, as shown in the image on the bottom right. By integrating SNNs into existing self-driving frameworks, we can take advantage of their fast, low-power processing for tasks like lane following. This allows us to test how well analog SNN implementations perform in controlled environments before scaling up to real-world deployment. Because SNNs operate efficiently under time-sensitive conditions, they have potential for broader use cases beyond self-driving cars, including robotics and sensory processing.
So in order to provide an overall proof of concept for our different iterations that you'll see throughout our project, we had to generate a way to consistently test the lane following and also how the car would respond to different models. It was recommended that we implement an error detection module, which was done via Raspberry Pi and Raspberry Pi camera. Some key concepts of this error detection module are the real-time lane detection, in which the camera and the Pi capture and process frames to detect lane deviations, ensuring accurate path following for the autonomous vehicle. The deviation and analyzation, you will see in the video demonstration that there is a point on the center of the line and then a line extending from that point to showcase the deviation visually, in which team members can retrace the steps of a car and see exactly where and when the EV deviated severely. For data verification and logging, there are timestamped deviation values stored in CSV files, which will enable post-testing analysis, ensuring data accuracy, which is a key concept of our project to ensure that our project succeeds, because data verification is a really big aspect of whether or not an iteration works or not. And that performance review is relating to like MP4 recordings and the deviation logs to allow us to evaluate system performance and optimize other things about the car. On the left is the line deviation, error detection, and then on the right is what the car looks like with the FPGA attached to it.
The way that the deviation program works is that a video gets sent from a Raspberry Pi to a main-based computer that runs MATLAB code that takes every single pixel on the screen compares the black-white value to a threshold and determines if it's above the threshold or below the threshold. This way, we could get a binarization of what is a lane and what is not a lane. From there, we can take the center point of the frame, determine that to be the center of our car due to the camera being stuck to the car, and we can see how far that center point deviates off the track. We could see from our testing and from our values that we collected from the CSV data on the bottom left, we could see that straight lines perform the best as they show consistent deviation and very low numbers. However, during sharp turns, we could see that it takes longer for the EV to react and to make the correct decision to stay on path. However, during the long right turn, we are able to see that the deviation has to reach a certain point at around 300 pixels, 300 pixels off, to be able to make that decision. And we could also see that it's fairly consistent with that data point, noting that it always makes the decision at a certain deviation.